Let's look at pulleys and when the string breaks or becomes slack. So the question says, two particles are connected by a light inextensible string. Particle A lies 4.5 meters from a small smooth pulley on a horizontal table, and particle B hangs freely with the string taut 0.5 meters above the ground. A force of 0.08 g opposes the motion of A, and the system is released from rest. A and B have masses 0.4 kilograms and 0.8 kilograms. Find the acceleration of the system, the time taken for B to reach the ground, and the distance traveled by A before it first comes to rest. And we have a diagram here which models the question. Now the first thing is we're going to annotate this diagram with all of the forces and the relevant information given in the question. So we know that both particles are connected by a light inextensible string, and this string must have tension acting in it. So for particle A, the tension in the string acts towards the right, and we'll label it as capital T, since this is the force that would be pulling particle A towards the pulley. We also have a tension in the string upwards that impacts particle B, since that's the force that's keeping particle B up in the air. Now the weight of both particles act vertically downwards, and weight is given by mass times g, where g is equal to 9.8. And so in this case, for particle A, its weight is equal to 0.4 g. Likewise, for particle B, its weight is equal to 0.8 g, and again, this acts vertically downwards. Because particle A is in contact with the table, it must have a reaction force acting upwards, and in the question we're told that there's a force of 0.08 g which opposes the motion of A, and so this force must act towards the left, which we'll mark on here. Because particle B has a mass which is greater than particle A, then we can assume that when the system is released from rest, B accelerates downwards and A accelerates towards the pulley. Since both of these particles are connected by a light inextensible string, then one of the modeling assumptions is that the acceleration is the same throughout the system. Now resolving forces, we'll start with particle A. We know that the motion of this particle is towards the right, and so we're going to resolve in this direction. Everything acting towards the right will be positive, and everything towards the left will be negative. And so we have T minus 0.08 g, which equals to 0.4 times A. And the way we get this is using F equals ma, where F is the resultant force, m is the mass of the particle, and A is the acceleration. Now if we resolve forces for B, we know that the particle moves downwards, and so resolving downwards, we have that 0.8 g minus T equals to 0.8 A, again using F equals ma. And so we have simultaneous equations here which we can solve by adding the two equations together. If we do this, we then have T plus minus T, which cancels the T's, minus 0.08 g plus 0.8 g, which becomes 0.72 g. And then we have 0.4 A plus 0.8 A, which becomes 1.2 A. And so if we divide both sides by 1.2, we end up with the acceleration equaling to 5.88 meters per second squared. And that is the answer to part A. And so we've added the value of the acceleration onto our diagram. Now part B says to find the time taken for B to reach the ground. And the way we're going to work this out is using SUVAT. So if we look at particle B and we consider SUVAT, since the motion of particle B is downwards, we'll take everything going down to be positive. And so we know that the displacement of particle B from when the system is released to when it reaches the ground is equal to the distance here, which is 0.5. We know that the initial velocity of particle B is equal to 0 because we're told that the system is released from rest. We don't know what the final velocity is of the particle B when it reaches the ground. We do know that the acceleration is equal to 5.88, which we worked out in part A, and then the time is what we're interested in for this part of the question. And so if we consider the values that we have and what we're trying to work out, we can use the SUVAT equation S equals ut plus a half at squared, and then substitute our values in to work out t. And so doing this, we have 0.5, which equals to 0 times t, which is 0, plus a half times the acceleration, which is 5.88 from part A, times t squared, where t is what we're trying to work out. If we multiply both sides by 2, we end up with 1 equals to 5.88 t squared, and then dividing both sides by 5.88 gives us 25 over 147, which equals to t squared. And then taking the square root of both sides, we end up with t equaling to 0.412 seconds, and this value has been rounded to 3 significant figures. Now in part C of the question, we want to work out the distance travelled by A before it first comes to rest. And so to do this, we first need to work out the speed at which B hits the ground. And so since we have the SUVAT set up from before, we can work out the final velocity using the exact values here and not the rounded value that we worked out for T, since this would result in an inaccurate answer. And so using V squared equals U squared plus 2AS, we get the following. So we're trying to work out what V is, and so we have V squared. And then we know that u is equal to 0, so 0 squared is equal to 0. And then we have plus 2 times a, which is 5.88, times s, which is equal to 0.5. And so simplifying this, we end up with v squared, which equals to 5.88. And so if we square root both sides, we end up with v equaling to 2.42483, and so on. Now when particle B hits the ground, the string breaks or becomes slack, and so as a result there is no tension in the string anymore. And so we now need to draw a new diagram for particle A and consider the new acceleration that we have. And so here's the diagram for when B hits the ground. So we can see that there's no tension in the string since it's either become slack or it's broken, and particle A is continuing to accelerate towards the right, towards the pulley, but there is no driving force. And so if we work out a new acceleration now, we have the following. So resolving towards the right, we know that there's no force acting towards the right, but there is the force resisting the motion of A, which is 0.08 g. And since this is acting towards the left, this must be negative. So we have minus 0.08 g, which equals to the mass of the particle, which is 0.4, times the acceleration, which is what we're trying to work out. Again, we get this using F equals ma. If we now divide both sides by 0.4 and taking g to be 9.8, we end up with minus 1.96 meters per second squared, which equals to the acceleration. Since this is negative, this tells us that particle A is decelerating, which makes sense in this context, since there is no driving force pulling particle A forwards. And so if we consider a SUVAT for A, when B hits the ground to when A comes to rest, we have the following. The displacement here is part of what we're trying to work out, and so we'll label this as a question mark. The initial velocity of particle A is equal to the final velocity of particle B just as it hits the ground. Because this string is inextensible, the velocities of both of these particles are equal as long as they are connected by the string. And so the initial velocity is equal to 2.42483, and so on. Now, since we're trying to find the distance traveled by A before it first comes to rest, we're considering when the final velocity is equal to 0. The acceleration of the particle is equal to minus 1.96, which is what we just worked out. And then the total time taken, we don't know. And so using v squared equals u squared plus 2as, we get the following. So the final velocity is equal to 0, and 0 squared is equal to 0. The initial velocity is equal to 2.42483, and so on, all squared. And then we have plus 2 times the acceleration, which is minus 1.96, and then times the displacement, which is what we're trying to work out. If we now square this value and then take this away from both sides, we end up with minus 5.8799 and so on, which equals to minus 3.92s. And now dividing both sides by minus 3.92, we end up with 1.499 and so on for s. And so rounding this to two significant figures, we end up with 1.5 meters, which equals to s. And so for the distance traveled by A before it first comes to rest, we need to remember that particle A travels 0.5 meters, and that is when particle B hits the ground. And so this displacement that we've just worked out is when B hits the ground to when A comes to rest. In other words, we need to add on 1.5 meters here to 0.5 meters, which was initially traveled. And so the total distance and the final answer here is going to be equal to 0.5 meters plus 1.5 meters, which when we add these together equals to 2 meters. And so that is the answer to part C.